14.33, the iodide ion reacts with the hypochlorite ion in the following way. And then it gives us a bunch of data. And first it says write the rate law for the reaction. So for here, what we want to do is compare two reactions, 1 and 2, where one of the reactants is held constant in concentration, and then the other one we figure out how much it changed. And so ignore the times 10 to the part right here, and notice that the initial rate right here doubles from 1 to 2. 1.3 times 1.3 is, 2. Times 2 is 2.7. So it doubled. And then you can see also that the concentration of OCl minus also doubles. Since the rate doubles when the concentration doubles, we say that it is first order. And so when we're writing the rate expression, we would say rate is equal to some constant K, OCl minus, and then that would be to the first power. Because if the rate doubles when the concentration doubles, we know that it's first power. Now we have to look at some different experimental data where OCl minus stays the same, but I minus changes. And so we can see in reactions 1 and 3, OCl minus stays the same, so that's out of the question now. And this goes from 1.5 to 3, so I minus doubles, and you can see that the rate goes from 1.36 to 2.72. Ignore the times 10 to them, you can see it also doubles. So when the I doubles, the rate doubles, so that means that the I minus must also be to the first power. So it's first order reaction, so there's our rate expression. Letter B, calculate the rate constant with proper units. So solving this for K, K would then be equal to rate divided by the concentration of OCl minus times I minus, to the first, both are to the first power. And then pick a reaction. It doesn't matter which one. I'm going to pick the first reaction right here. And in the first reaction, I'll put in the rate right on top here, 1.36 times 10 to the negative fourth. And the units on that are molarity per second. And then I'll put in the OCl minus, which is 1.5 times 10 to the negative third molar. And I'll put in the I minus, which is also 1.5 times 10 to the negative third molar. And then looking at the units here, we can see that one of the molarities would cancel with one of the molarities right here, and then we're left with seconds times molarity, both to the negative 1 power here for our units. And then the division right here of that ends up being 60.44 for our numerical value of K. Then in letter C, it says calculate the rate when, and then they give us two values. Since we know the rate constant now, we can plug these values into the rate expression and solve for the word rate. So rate would be equal to 60.44, 1 over seconds times molarity, and then we'd multiply that times the molarity of OCl minus that they give us right here, which is 2.0 times 10 to the negative third molar, times the concentration of I minus, which is 5.0 times 10 to the negative fourth molar. I'm running out of room here. Okay, anybody would see one of the molarities cancel with one of the molarities, so we're left with molarity per second. Multiply all those guys together there in letter C, and we'd end up with 6.0 times 10 to the negative fifth molarity per second for number 33.